Now today I'm going to report on a paper that past and recent results on maximal data information priors. Now this came up, I started work on this in the 1960s, 1968. I tried to get a crisis. Yes. Yeah, it's in the package you have. So I tried to get a criterion functional that you could optimize to provide prior distributions in a formal, reproducible way. That's very important to get a good prior, there's no question about it, good prior, but also to have it reproducible. You know, some subjective Bayesians, personalists in particular, will say, we don't want formal techniques. They criticize Jeffreys for having a formal technique to produce priors. They want to do it subjectively. See, that's hard to sell in science. If you report that... Oh, stand. Okay. So, as I say, it's very important to have a reproducible way of producing both diffuse and informative priors. Jeffreys was the first to give a procedure for doing that. And ever since he's produced this procedure, alternative procedures have appeared. It's almost like the automobile industry. A Ford, a Chevrolet, Honda, different procedures for producing priors. So we're all competitive now. I'll mention different procedures and try to convince you that this procedure deserves your attention. And then it just occurred to me yesterday that this procedure for producing prior distributions for parameters can also be used to produce random, when you're in a random effects non-Bayesian setup, you need a distribution for the random parameters. This procedure will produce a distribution for non-Bayesians who use random parameter models. So it's funny as hell. Okay, now in the overall picture, as I mentioned the other day, of information theory and Bayesian statistics, this is an area that's developing very rapidly. Information theory, and you have references in that first paper. Information theory, I'm going to use it to produce prior distributions today, but it can be used to produce models for the observations, information provided by an experiment based on the Bayesian method of moments, and a number of other applications can be done. Okay, now here are selected references that are given in the paper. Cass and Wasserman and Jassa have a 1995 review paper on procedures for generating priors, the different procedures that I'll mention. And here are some other references that I won't go into in great detail here. And the paper has introduction, general properties of the approach, the information, criterion functional, derivation, subject to side conditions, invariance considerations, some applications, and you can also produce odds for hypothesis testing. Posterior odds require the prior odds. How do you get the prior odds? This procedure yields optimal prior odds. And as I say, general applications and so forth. All right, so as I say, the following procedures have been put forward in the literature. First, you had Jeffreys' procedure. Secondly, Ed Jaynes suggested a maximum entropy approach to produce priors. Then you had, I actually conceived this one in '68, so I would say third is mine. And then fourth, Bernardo worked with Lindley and produced the Bernardo approach in the early '70s. And then Berger and Bernardo teamed up to produce the reference prior approach. And then there are one or two other approaches around for producing priors. These are some of the major ones where you derive the prior from a criterion functional. Because you set up like a profit function in economics. You want to get the inputs that maximize profits. Here we'll have some criterion functional, and we'll try to get the prior that optimizes the criterion functional. Okay, now we start with a definition of the information in a joint density. We have a joint density of a vector of parameters and a vector of observation, P of y and theta. You saw that in several of the lectures earlier. Now this is what's called the negative entropy. H is the entropy, minus H, some writers, some consider that to be a measure of the information in a density function. Now simply put, you look at this, this is just the average log height of the density. So you're integrating the log of the density times the density. So that gives you the average log height. If the average log height is great, the density has a lot of information. If it's low, flat, little information. So you compute this, you can compute it for a wide range of densities, normal, student T, whatever. These things have been tabled. So you can look in the tables of entropies, and for different density functions, they've tabled the entropy function. But this then is what we'll call the information in the joint density of y and theta. And now we can break up the joint density into a marginal, that's the prior, pi of theta, times the data density, f of y given theta. This is the product rule of probabilities. And I refer you to Jeffries and his consideration of the proof of the product rule of probabilities. Set A, set B, the intersection of A and B, the points in A, B, and the intersection are equally probable, and then you derive the product rule. He has that as a theorem. And then he said the points are assumed equally likely to be drawn. We're going to be using the theory where they're not equally likely to be drawn. So he introduces the product rule as an axiom. And you heard the other day Professor Polasek mentioned Laplace assumed the causes, A1, A2, A3, equally likely. I thought somebody was going to jump up and say, many times the causes are unequally likely. So there's a need to generalize the product rule of probability. Now I'm working on that. Who knows, maybe I'll get a solution. But the case where the points in the set A, B, and the intersection have different probabilities of being drawn. So what would be the analog of this when the probabilities are not equal? Well, let's leave that for the future. So if we just substitute that in here and do the integration, this expression breaks up into two parts. The first part, you have I of theta times pi of theta, pi is the prior, d theta. I of theta is the information in the data density. See, that's the integral f of y given theta times log f of y given theta. That's the average height of the data density, and that's a function of theta. So I call that the information in the data density. And then here we have the information in the prior. The integral pi log pi of theta d theta. So the total information breaks up into two parts. The average information in the data density, average with the prior, plus the information in the prior. I almost feel like stopping at this point because this is a very nice breakup. And also, if you subtract this from this side, remember this side is the total information, you get the information provided by an experiment. So this part is the information provided by an experiment. The information in the joint density of y and theta minus the information in the prior. That gives you the information provided by the experiment. Now I should tell you that's a different definition from the definition in the literature due to Good and Lindley and others. They define the information in an experiment as the information in the posterior minus the information in the prior. This is a broader definition, as I'll show you. Now, the question is, what do you want to feature in your analysis? I think we want to feature the information in the data. So we want to have a criterion functional that features the information in the data. So we'll just take the difference of these two terms. This one minus that one.
Can we not maximize that function itself, the sum itself, instead of the difference?
You can maximize the sum of them, yes. But that doesn't yield the general distributions. But you can do that, right. Now, what I thought you want is, here is the information provided by the experiment, or the information in the data density, minus the information in the prior. So this is the criterion functional I'll use. Now I should tell you I'm defining here entropy relative to uniform measure. Okay, uniform measure in defining the entropy of the prior density. Okay, so there's the criterion functional. And the problem is, can we give it a different interpretation? Well, if we break up the joint density into a marginal g of theta given y times a conditional h of y and put it into the expression, this becomes this. Now this is the likelihood divided by the prior. And g of theta will be the posterior distribution. And by maximizing g of pi with respect to pi, we're maximizing the average log height of the likelihood function relative to the prior. So you see, if you maximize the sum, you wouldn't get this. So you want the likelihood function to be featured. And when you choose the prior according to this criterion, you're trying to make the expectation of the log likelihood to the prior as great as possible. So that's another interpretation of the criterion functional. Now a third thing you can do with a little algebra is to relate g of pi. G1 is the information provided by an experiment as defined by Good and Lindley. The entropy of the posterior minus the entropy of the prior. And this is equal to that plus another term. And this is the entropy of the marginal density of the observations. If you just consider the posterior distribution, you're not considering the total output. Another output of the process is the marginal density of the observations, h of y. There's information in h of y that we use for forming Bayes factors and things like that. So g of pi is broader than g1. Now I worked for 2 months or a month and a half trying to maximize this G1, the entropy of the posterior minus the entropy of the prior, way back in the 60s, and the solutions don't come out easily. Have you ever tried working with that? It takes you 6 months to derive a prior. It's terrible. I was in South Africa in '98. Dan Duval was working on generalized extreme value distributions, trying to maximize G1, get out a reference prior. He and a very good colleague spent months and they couldn't get the derivation done. And so I came along and suggested this approach. As you'll see, the solutions come out very easily. Within an afternoon, they computed the prior distributions provided by this approach. And they were very happy with them. Okay, so as I say, g of pi is equal to the information provided by an experiment plus the information in the marginal density observations minus the information in the prior. So this is broader. And this is a concave function, and this is a concave function. So if you maximize this, you can actually express it in terms of an average of a sum of 2 functions. This one and the one that maximizes the entropy of the prior. So you can look at it that way. Sufi made that point. Okay, now we want to get the solution to that problem. Okay, so let me show you the problem again. Here is the criterion functional, and we want to maximize g of pi with respect to pi, subject to pi's being proper. Pi integrates to 1. So I'm using a compact parameter space. Now there's been a lot of discussion in the literature, should the parameter space be compact or not? Some people think it should be compact, others think it should be unbounded, improper, etc. If you get the compact space broad enough, the differences are trivial, really. So if you want to discuss that later, I'll be glad to come back to that. But I am assuming a compact parameter space. Now, when you do a calculus of variations analysis of this criterion functional, subject to side conditions, use just one side condition, the prior be proper, the solution that comes out is right there. So the optimal prior is a normalizing constant C times the exponential I of theta. And as I mentioned, I of theta is the negative entropy of the data density. So here's I of theta. So you have your data density. You compute I of theta, or look in the tables, because these are tables, and then you just plug that in to this expression, and you get your prior. If you use just the side condition that the density be proper. Okay, so that is the way you generate the priors. And I'll show you applications of this to the standard problems. You have tables in the paper, location problems, regression problems, and whatever. Okay, now you can also, if you do some algebra, express the optimal value of g of pi star, minus g of pi star equals this integral. And this integral is called the cross entropy, the distance between pi of theta and the optimal pi. So when you take pi of theta equal to pi of theta star, this attains a maximum. So that's a way of showing that you've got a maximum and not a minimum. There. Now if you put side conditions on the problem like this, maybe you want to assign a mean. M1 is the first moment of theta. M2 would be the second moment around 0. M3, the third moment around 0. MQ, the qth moment around 0. So then you optimize G, subject to these side conditions and subject to its being proper, and you come out with an expression that looks like this, but plus lambda 1 theta plus lambda 2 theta squared plus lambda 3 theta cubed and so forth. And then you have a procedure for evaluating Lagrange multipliers that I mentioned in the paper. So you can tack on these side conditions and get informative priors as well as uninformative priors. Okay. Now let's see how this works in practice. Here's some standard problems that I worked many years ago. All right, here is a normal location parameter. This I of theta, if you compute integral f of y given theta log f of y given theta d theta, turns out to be a constant. So e to the I of theta is a constant. So this says be uniform on theta over a wide finite region. Now if you have just a scale parameter, normal, you compute this integral I of theta, you get I of theta equal a constant minus log of sigma. E to the log of sigma gives you 1 over sigma. E to the minus log of sigma, you get 1 over sigma. Now if you have both the location parameter and the scale parameter in the problem, the I of theta comes out to be a constant minus log of sigma, and this is the prior, 1 over sigma. Now these are the standard priors that most people use for this problem, diffuse priors. Jeffrey's procedure gives you 1 over sigma squared, and he then changes the procedure to get 1 over sigma. It's too invariant, he claims, so he applies the procedure separately to the location parameter and the scale parameter and comes up with 1 over sigma that he considers more reasonable. Okay, now suppose I gave this talk at Yale a few years ago and Hartigan was there. He proposed, how will it work on the rectangular distribution? I said, oh, I hope it works okay. So Here's the rectangular distribution. So you have y given theta is 1 over theta. Y goes from 0 to theta. So theta defines the range of y. Y equals that. Okay, when you compute this I of theta measure is a constant minus log of theta, and the density is 1 over theta. So that comes out very readily. Now here you have the exponential, or the Pareto distribution. And you compute this I of theta measure, it comes out to be a constant minus log of theta, so you get 1 over theta. Now this is in agreement with Jeffrey's procedure. The parameter that goes from 0 to infinity, you take the log uniform. So that's true for sigma and this parameter. Okay, now you have the student T density. Some people like to assume the observation student T, particularly in stock return data. The data aren't normal in the stock market. And they're not student T either, by the way. They're heteroscedastic. But early in the game, people did use IID student T assumptions. And guess who used them first? Jeffries. In geophysical data, they noticed the tails were heavier than the normal. So old Jeffries worked the problem IID student T rather than IID normal. And so when you use this for known degrees of freedom, the prior comes out to be uniform on theta and log sigma. So you get 1 over sigma. Now, I mentioned in the paper that I distributed that some have solved for a prior on the degrees of freedom as well, using this approach. I haven't included that here, but I give you a reference to the literature. Sufi and independently Moulton derived the maximal data information prior for nu. Now here's the log normal distribution. You know, incomes are sometimes log normal, etc. So you have this as the data density, and theta is the median of the distribution. And when you compute this I of theta, you get this expression, and e to the I theta gives you 1 over theta. So this gives you a prior, and there should be a sigma over there, 1 over theta times sigma. I'm sorry, modify that. Should be a sigma there. You see the log sigma here. So when you raise this to the power e, you get theta times sigma. Okay, now you can also apply this to general forms. So here's a general location class of densities. Here's a general scale class of densities. And here's a general location scale class of densities. This would include the normal, the student T for given degrees of freedom, etc. When you compute the I of theta, and you can do this analytically, okay, and then the exponential class, if you want to solve that one, you can get a prior for the general exponential class. I haven't analyzed this too much, but you can solve it for the general exponential class. Okay, and here's the thing I was looking for before. With the side conditions on the means, the moments, you get the posterior distribution like this. Exponential I of theta. Now here's the first moment condition, the mean. The qth moment condition gives rise to a Lagrange multiplier, lambda sub q times theta to the q. So this is an informative prior. Or it could be, from a sampling theory point of view, a density for the random parameters. Okay? And you have to evaluate the Lagrange multipliers. This paper provides you with an algorithm for evaluating Lagrange multipliers. So the numerical method for evaluating Lagrange multipliers. Okay, now you can also use side conditions. For example, suppose you want to designate the median, a prior median. Then some physicists at a meeting at the University of Wyoming years ago suggested using delta functions to define the median. So suppose theta goes from A to B, and this delta function is 1 up to m and 0 beyond m. Then this defines the median, m. That this integral is equal to 0.5. So then you can use this as a side condition and get the maximal data information prior looking like this. And you have a Lagrange multiplier here times the delta function. And I show you an example here where you can compute a prior subject to a condition on the median. Then if you have a condition on the interquartile range, you can express that using delta functions and come up with a maximal data information prior with a given median and a given interquartile range. Now, I don't think the other procedures I mentioned can do this, to have quantile restrictions. This works out fairly directly. The only thing you have to do is evaluate the Lagrange multipliers. Okay. Now, if you want to use some other measure in defining entropy, here's the entropy relative to the measure m of y and theta. Okay. And I'll just say, because I don't want to spend too much time on it, and it's in the paper, that you can go through the operations we went through before and get the maximal data information priors for a g that's defined using that measure. So you get, I'll try you this. You can break up the integral looking like this into two parts, and then this Im of theta is now this expression. It's f of y given theta log f of y given theta and the measure on y given theta. Okay, and here we have the prior with the marginal measure on theta. So the criterion, the total information breaks up this way. The criterion functional is this one minus this one, this minus that. And then the general solution subject just to a normalizing condition is a constant times exponential Im of theta. And Im of theta is this. So if you want to use other than uniform measure, you can put in your measure function and solve for the prior relative to that. Okay, now the problem came up earlier in your question. If you have different parameterizations, how do you get invariance? Okay, this question of invariance came up very early in the game. I mentioned in the paper, student wrote a paper on a location problem, and he used the uniform prior. He sent his paper to R.A. Fisher. R.A. Fisher said, you're uniform on theta, but you're not uniform on theta to the fifth power. And a student wrote back to Fisher, I don't care about theta to the fifth power. It's an irrelevant parameter. Okay? Now, Jeffrey's prior is invariant to all one-to-one continuous transformations of the parameters. So if you use Jeffrey's prior, you're invariant with respect to all one-to-one parameterizations of the prior. That means if you parameterize a problem a particular way and use Jeffrey's prior, I use a different parameterization, as in this log normal case. You use Jeffrey's prior, we'll get consistent probability statements. If the priors are not invariant, we won't get consistent outcomes. So it's very important, and Jeffreys was the first to emphasize this invariance property and produce priors that are invariant to respect to all continuous one-to-one transformations. Now, in some problems, Jeffrey says that's too invariant. So he wants invariance with respect to a subset of transformations. So he changes his criterion function very sensibly. And then C.R. Rao, I quote him in the paper, he said, some problems you don't want invariance. And other people say, how much invariance? Berger, for example. The problem is how much invariance to build into a problem. The citations are in the paper. And my position on this is you want to be invariant with respect to relevant transformations. As students said, theta to the fifth is an irrelevant transformation. I don't care. You want to be invariant with respect to relevant transformations. Okay, so that's the point of view I've taken on this. And when you have different parameterizations, you define this G for each parameterization. and you take the sum of the g's. And then to get invariance, you put on a side condition which gives you invariance. Okay, the side condition shows you the type of invariance you want to get. So you maximize this G subject to a side condition, given that the densities are proper, and given that they satisfy a side condition, an invariant side condition. And out comes this solution. Okay, suppose we have A to I equals H of I theta. I equals 1, 2 to Q. We have Q continuous transformations. So theta goes to A to I. Okay, and this H prime, this is involved in the Jacobian of the transformation. So this generalized solution, here's the solution that's invariant with respect just to linear transformations. When you have nonlinear transformations, you get another term in here to provide invariance with respect to this set of transformations. Okay, so that's the way you generate. Now one application would be, suppose theta is a regression coefficient and eta equals 1 over theta. That comes up in the Havelmo model that you've all studied. You can parameterize the problem in terms of the multiplier or the marginal propensity to save in the simple consumption model that Havelmo analyzed centuries ago. Okay, so you want invariance there because you're going to make that transformation. So when you apply this procedure, you get the G for the problem parameterized in terms of eta. You get the G for the parameterized, the problem parameterized in terms of theta, and then you get the Jacobian of the transformation. And this yields the prior 1 over theta and 1 over eta. And these are invariant. So you have this class of transformations, you'll get consistent probability statements for the different parameterizations. Okay, now you take the uniform prior on theta, you get 1 over theta squared as the implied prior for eta. If you make the transformation from theta to eta, here's the implied prior. That's very different from 1 over theta and 1 over eta. Okay, so if you do this to powers of a scale parameter, log of sigma, sigma to the first power, sigma to the second, sigma to the nth power, and you come out with the solution, if you apply this procedure, 1 over sigma. And that's invariant with respect to powers, as Jeffreys showed many years ago. So that yields the Jeffreys prior, invariant with respect to powers. Okay, so this is a way of approaching the question of invariance. And you, for example, later in the paper I mentioned you want a prior on a covariance matrix. If you're not going to make any transformations, you get 1 prior. If you're going to transform from sigma to sigma inverse, you want to be invariant with respect to that transformation. And you can see in the paper how you get the invariant prior on sigma this way. Okay, so the important point here is that this approach enables you to derive diffuse and informative priors that are invariant with respect to relevant transformations. It's very important that you have a procedure that gives you invariant results if you're going to make transformations. Otherwise, one person works with a prior in this parameterization, another person works with a prior in this parameterization, you get contradictory results. You want to be consistent over the transformations of the parameters that you're going to use. Irrelevant transformations, forget about them. Just the relevant ones. Okay, that I think is very important. Okay, now how can you link up this procedure to other procedures? First, you can change this G function. You can measure W times I of theta, that's the information in the data density, 1 minus W times the log of the determinant of the Fisher information matrix. That's another measure of information, minus the information in the prior. And you can vary this expression with respect to the prior, subject to its being proper. And the solution that comes out is the determinant of the Fisher information matrix to the 1 minus W over 2, e to the W I of theta. So you get a combination of the Jeffreys prior and the maximal data information prior this way. Okay, but the thing is, here we've changed the criterion functional. And we're using two different measures of information in the same function. Mathematically it goes through, but it's disturbing from a conceptual point of view. So if we go back to the earlier criterion functional, the G, and we maximize it subject to the side conditions. Here is the expected log Fisher information matrix to the 1/2 power equals C1. Here's expected information in the data density equals C2. We maximize the original G subject to these two side conditions, and the side condition that the prior be proper. We come up with a prior that looks like this. The determinant of f to the lambda 1 over 2 times e to the lambda 2 times I of theta, where lambda 1 and lambda 2 are Lagrange multipliers for these side conditions. So this is the form of Jeffreys prior. This is the maximal data information prior. And then when you can look at it both ways, some person cooked up a generalized max entropy prior that takes this form. Rodriguez is a citation. There's a reference in the paper to generalized maximum entropy priors. So this is in the form of the Rodriguez prior. So as I say, you can put on all sorts of side conditions and get solutions reflecting the information you want to put into the problem. Very important. Okay, now we go on to data density and mass functions. Okay, so here we have a number of problems I've considered. The rectangular density I mentioned to you, the exponential density we've looked at already. Let's go on to the binomial. Oh, well, in this paper I did with Sinha, we have the Weibull density. You'd be interested in this, given your background. There's a lot of controversy about how to take the priors for the parameters of the Weibull density. Now, if you parameterize the density like this, the parameters are gamma and theta. And this is the prior that comes out of this approach. So with theta and gamma, you use 1 over theta and 1 over gamma. And with gamma times e to the minus this constant, Euler's constant, times gamma. So this is the form of the maximal data information prior for one parameterization of the Weibull density. Now if you use a different parameterization and you want to get consistency, you use the approach I mentioned before. So we consider different parameterizations, and you can compare this with the Jeffreys prior. It's somewhat different from the Jeffreys prior. Okay, now what about probability mass functions? Take the binomial. Now we had talks about the binomial distribution for several days. Everybody used the normal prior for that binomial parameter, or most did, as the diffuse prior. There's a little controversy about what should be the prior for the binomial parameter. Jeffrey, Laplace, and Bayes used the uniform prior. The Jeffreys prior isn't uniform. It's 1 over theta times 1 minus theta to the 1/2 power. It's a proper beta density that goes off to infinity at 1, and it goes off to infinity at 0. The Haldane prior is 1 over theta times 1 minus theta. That's an improper prior that goes off to infinity at 1, off to infinity at 0. When theta goes to 0, it goes off to infinity. Those priors put a lot of mass around 0 and 1, as Jeffreys noted. He studied these things very intensely. So his prior went off to infinity too. He's very honest. He says, I don't like it going off to infinity. Let's see what the maximal data information prior approach yields. We solve that maximized G, subject to theta, the prior on theta being proper. So we get the I of theta for the binomial is exponential log f of y given theta. And that gives theta times log of theta plus 1 minus theta times the log of 1 minus theta. You see, here's the binomial mass function over here. The binomial mass function. Y is 0 or 1. You log that and take the expectation. The expectation of y is theta. The expectation of 1 minus y is 1 minus theta. So this gives you the information in the probability mass function for the binomial process. One observation. Oh, we take e to the I, and this is the function that comes out. Theta to the theta, 1 minus theta to the 1 minus theta. What a beast. This at 1, the limit of this is 1.6. It starts at 1.6. It has a minimum at a half, and then it comes up symmetrically to 1.6 at 0. So instead of going off to infinity, it's at 1.6 at the endpoints. It's above the uniform at the endpoints, but it doesn't go off to infinity. So this function meets the objections that Jeffries had for the uniform. Now Kaiki too, from Japan, Akiyiki, he too didn't like the uniform, and he didn't like going off to infinity. So this one gives you something that's symmetric around 0, a little extra probability at the endpoints, because it's always possible when you're flipping a coin. For example, I flip a coin fairly, it comes down heads. What's the probability of a tail on the next flip? Everybody says 1/2. I tell us in Chicago, you're in Chicago, it's a two-headed coin. You see, it could be a two-headed coin. There's a certain probability there. So you want to take that into account. And you know, when you're studying a particular species of plants, they may be all of one type. Or if you're testing a theory, you get 1 success, 2 successes, 3 successes. It could be the theory is right. Every time you test it, it comes out correct. This is the Laplace rule of succession. And Jeffries didn't like the Laplace rule of succession because it didn't go up more rapidly. The mean of theta, as the number of successes increases, didn't go up rapidly enough. So in one part of his book, he piled some probability on 0, some probability on 1, and spread the rest uniformly 0 to 1 to get the mean to go up more rapidly. Because he found in practice, when you're testing a theory, if you get 1, 2, 3 successes, you go up toward 1 very quickly, rather more quickly than the Laplace rule of succession would have you do. So this is the prior, and you can use this easily. You can expand it around to half if you like, use an approximation to this and integrate it, or use a univariate numerical integration to get the marginal densities and so forth. So this is a brand new distribution that came out of this approach. And of all things, it's proper, but it's very hard. If any of you mathematicians out there know how to integrate this function analytically, you'll be famous, really. This is a hard integral to do. Well, I've spent hours on it, so if you get a solution, please let me know.
Did you try it in mathematical?
Oh, numerically, there's no problem.
Mathematical does symbolic computing. So if there is a closed sum solution, we'll possibly split it out.
I see. Well, I know there isn't an explicit solution, because even integrating x to the x, you don't do it, you get a series expansion. That's in the tables of integrals. So this is more complicated than x to the x. So it doesn't lend itself to a analytical solution. Okay, now, what about a trinomial? Okay, when we use this approach, here's the density function that comes out for the trinomial. You get theta 1, theta 2, and 1 minus theta 1, theta 2. So it's in the same form as the binomial, but now you have 2 parameters. So here you get a rectangular region, and then you have contours bowl-shaped. Comes up to a finite value at the region, and a minimum at a third, and a third. So a bowl-shaped, this is the surface, is bowl-shaped. A minimum at theta 1 equals a third, theta 2 equals a third, 1 minus theta 1 minus theta 2 equals a third, and then it rises up to the triangular, at the border of the triangular region, comes up to a finite value, the bowl-shaped prior. Now if you have a multinomial, you have theta 1 to the theta 1, theta 2 to the theta 2, theta m to the theta m. Theta m is 1 minus theta 1 minus theta 2 minus theta 3, and so forth. Now in the paper I show you what comes out of the Jeffreys approach on these problems, what comes out of several other approaches, and this, as with the binomial, I think is much more reasonable. In the multinomial problem, it's hard to decide on what the diffuse prior should be. A lot of controversy there. Okay, now let's look at some univariate linear models. Let's take the regression model. yi is xi prime beta plus ui. Standard linear regression, multiple regression. Beta's the unknown parameter. Here we'll make a normality assumption for the error term. Sigma squared is the variance of the error term. Error term is mean zero. We want a prior for beta and sigma. Okay, here is the density function of y given x. As you well know, we log this and take the expectation. And that comes out to be log of sigma plus a constant. So e to the log of sigma plus a constant gives the prior. So you take the elements of beta uniform and independent of sigma and log sigma uniform, 1 over sigma. This is the standard prior. And you get it out in one line, essentially. So this is pretty much the standard prior.
So one question. Even there you are assuming, although of course it's coming out free of beta, but still restricting beta to a compact space.
Yeah, a very large compact space, unless in economics, as you know, many times we have restrictions on these parameters. The parameter doesn't make sense if it's outside the range 0 to 1, or if it's negative. So you can put restrictions on the parameter space to restrict the elements of beta 0 to 1. And then you get a rectangular distribution for the elements of beta defined over the relevant regions. That's very important. In certain time series, if this is a time series problem, you may want to impose stationarity, an AR1. You would do this -1 to +1, okay? If you have the initial condition fixed. Okay, so this is the regression model. Now if you add moments of beta, you can then get the solution subject to given moments of beta. And you get, say, if you have 2 moments on the beta vector, this yields a normal prior. Normal but truncated over, defined over a finite region. So that works out very well. Okay, now what about a first order stationary process? This we heard about yesterday. Here is a parameterization of the first order AR process, stationary. Beta is the mean of the process. I'm sorry, theta is the mean of the process. Beta is the coefficient of yt minus 1. And the absolute value of beta is 1. Okay, here's the data density. F of yt given beta, theta, and sigma. And this you would do if you used a random initial condition. Okay, so that looks like this. Then you log it and take the expectation. And this is the expectation of log f. That's the information in the data density. E to this gives you this prior. Okay, so with respect to sigma and beta, they're independent. The prior on sigma is 1 over sigma. The prior on beta, the coefficient, is 1 minus beta squared to the 1/2 power. So it has a maximum over 0, and it comes down to 0 at 1, and it comes down to 0 at -1. So it's like this. Okay? Now, the Berger-Bernardo reference prior approach doesn't yield this, as I mentioned down here. What they get is 1 over sigma times 1 minus beta squared to the 1/2. Here it is. And they said that is the same as the Jeffreys prior. Therefore, it's good. But they didn't read Jeffreys on this prior. When you read Jeffreys on this prior, he derived it. But he said it's no good. It goes off to infinity at 1. When beta is 1, the denominator is 0. So it goes off to infinity at beta equals 1. That puts a lot of mass around 1. And it goes off to infinity at minus 1. So Jeffreys writes, that's bad that it goes off to infinity at 1. That it goes off to infinity at minus 1 is intolerable. And I'm quoting him. He's very honest. He gets something with his method he doesn't like. He tells you he doesn't like it. Berger and Bernardo hadn't read that part of Jeffreys. So they said it was good because it was the Jeffreys prior. So this one, I think Jeffreys would like. Because stationarity means beta isn't equal to 1, and it isn't equal to minus 1. So you have 0 density at 1 and minus 1, and the mode is over the 0 value. The simplicity postulate would say the simplest model is beta equals 0. So you put a little extra probability in the vicinity of 0. Okay, now for a stationary AR2 process, you have yt minus theta. Theta is the mean of the process. Rho 1 times yt minus 1 minus the mean. Rho 2 times yt minus 2 minus the mean plus the ut. And if we assume ut is normal 0 sigma squared, you could make other assumptions, but this is the standard assumption. The mean of yt is theta, the variance of yt is this expression. Okay, and then if you use this approach, in this paper we show that the prior density yielded we're just assuming the density is proper, it comes out in this form. So 1 minus rho 1 squared minus rho 2 squared minus 2 rho 1 squared rho 2 over 1 minus rho 2 to the 1/2 times sigma. And when you plot the contours of that density, there it is. This is the region of stationarity. Here's rho 1 and here's rho 2. And these are the contours. It comes down to 0 on the boundary, just as in the AR1 process, and then it rises to a mode at 0, 0. And these are the contours. It falls off to 0 on the boundaries. I wouldn't have bet on this looking at that function, but that's the contours of the function. So this is then for a stationary AR2 process. Okay, so that is very reassuring. And when you get to an AR2, if you use a uniform prior on rho 1 and rho 2, you won't get contours like this. Okay, so a uniform prior on rho 1 and rho 2 won't give you contours like this. Further, a uniform prior on rho 1 and rho 2 has great implications for the roots of the process. Now, just draw from the uniform prior and compute the roots for each draw. And you'll find, as we did some years ago, there's about a probability of 0.8 or so that you get 2 complex roots and 1 real root if you use a uniform prior. And then for the 2 complex roots, if you compute the period of the oscillatory component and the amplitude, there's a high probability the amplitude is less than 1, and the mean of the period is roughly 4 to 5 years. So for business cycle analysis with a 4 or 5 year period, the uniform prior is not too bad. This will have other implications for the roots. So if you're interested in the roots of the process and the AR parameters, this hasn't been derived yet, you want an invariant prior for those 2 parameterizations. You can parameterize it in terms of the roots of the process, or row 1 and row 2. Oh, I'm sorry, this was for an AR3, where we had 3 roots. So you can do this uniform, and for each draw, decide whether the 3 roots are all real, or 2 complex conjugate and 1 real, and do the analysis I mentioned before. For the AR2, you either have 2 real roots or 2 complex roots, and you can do the same analysis here. Okay, now let's get on to the Stein problem. There's a great question about how to take a diffuse prior on n means. So you have a vector of means, y is a vector of observations, zeta is a vector of means, and u is a vector of error terms. Now Stein assumed the u normal with mean 0 and covariance matrix I sub n. Now this is something Stein slipped over on everybody. He assumed the variance known. If the variance is unknown, the parameters aren't identified. You have n plus 1 parameters and n observations. So he was using prior information to assign a value to sigma squared. So it's remarkable. So I'll go along with Stein and assume sigma squared is 1. Okay? Now how do you get a prior on the vector of means? Okay, one way to do it, and then also how do you obtain a prior on the sum of squared means? This is a non-centrality parameter. Okay, so this is a hard problem. If you use the Jeffreys prior on the means, and that's uniform, and derive the implied prior on theta, you get something crazy. So if you use a uniform prior on the etas, you get a crazy prior on theta, and when you make inference about theta, you get crazy results. Look at Berger's book on statistical decision theory. He shows this very clearly. So you have to get an appropriate prior to make good inference about theta. See, if you're uniform on the means, you're not uniform on theta. Okay, so you have to parameterize the problem in terms of theta and the angles. So you go to spherical coordinates, as Good and Wallace suggested many years ago. Look at the problem in spherical coordinates. Instead of Euclidean space, transform from the n means to a radius vector and n minus 1 angles. So here's, in the spherical coordinates, the ith mean is the square root of theta times the cosine alpha 1 cosine alpha 2 times the sine of alpha n minus 1 plus 1. So you can write eta I as a function of theta and alpha. And then the density function in spherical coordinates works out like this. Y prime minus q prime y minus q over 2. Okay, so the information in this data density, we compute the I of theta and the angles, is a constant. So this maximal data information prior tells you to be uniform on theta and uniform on the angles. Now if you're uniform on theta and you're uniform on the angles, you're not uniform on the means. You can transform back to see what you get as a prior on the means, and that gives you something very close to the prior that Stein used to get his optimal shrinkage estimates. Okay, so that's a very difficult problem and solved very nicely when you go to polar coordinates. Now if you're going to work both in Euclidean space and spherical coordinate system, you want to be able to be invariant with respect to the transformation from the vector of means to the radius vector and the angles. I haven't worked that problem yet, but the procedure I showed you before, when you set up G for one parameterization, you set up G for the other, you compute the Jacobian of the transformation, you can then get an invariant prior for that. I haven't worked that out, but that could easily be done. Okay, in summary then, let me just finish off. We have a procedure that seems to work reasonably well over a range of models and problems. You can incorporate invariance considerations. You can get prior odds that are optimal. You can formulate these optimization problems subject to side conditions and produce not only diffuse priors, but informative priors. Now, the Jeffreys procedure, the Bernardo-Berger procedure, they can't produce, as far as I can see, informative priors. And then the Berger-Bernardo procedure doesn't give you analytical solutions very easily. You have to spend a month or 2 or 3 to derive a solution, and then it's only an approximate solution. They use an asymptotic approximation. I mentioned that in the paper. So if you want to consider that, asymptotically, who knows what's going to happen to your model. So not getting the exact solution is really bothersome. Now, there's no question that you can modify the criterion functional in different ways and solve other problems. You can change this G criterion functional and get other information theoretic priors out. So this is a start on the problem, and I think you can easily generalize it and apply it to many different problems. So I feel fortunate to have stumbled onto this procedure. You have to be lucky in research. You stumble onto something and you hope it works. But this is, as I say, a very controversial area. In the literature, people fight about these different priors. So keep in mind, it's very controversial, and you want to compare the results of this procedure with other procedures and make up your own mind about which procedure is best or better in producing usable, useful prior results. Well, thank you very much, and thank you for your good questions.